Hello, welcome to our science show today. And today we are discussing a very interesting topic, which is Hubble tension. So that means that the expansion of universe, and this is a unique and mysterious aspect of cosmology. And we will together, Chandrakant and me, will be discussing regarding this feature, where a lot of research is going on. So, Mr. Chandrakant, what does it mean when we say Hubble tension?
Well, good morning, everyone. Good morning, Kanchan. And you see, our whole physics is dependent on there was a Big Bang, and we know that there was a Big Bang. And since the time the Big Bang happened, which was about 13.8 billion years back, universe has been constantly expanding. And since we are expanding, the entire physics is dependent on this understanding that there was a start and there is going to be an end, or maybe the end will not happen. It will be a perpetual continuous journey. And so this was the basic understanding. But later there was a gentleman called Edward Hubble, who actually from his home base observatory found that there is something else going on in the universe in the year 1920, etc. And he found that it is we are not only expanding, but the expansion is accelerating, which is, as the time passes, the expansion is increasing exponentially. So when we say that it is accelerating, that means it is every passing moment the expansion is greater and much greater. So initially the motion of the universe was slower, but as the time passes, it is actually increasing. Now, this is very surprising. Simply if you look at the applied sciences today, whenever you have a big explosion, the initial explosion expands quickly soon after the explosion, and after that it cools down and then slows down. Whereas in the case of universe, the Big Bang was a big explosion, and the explosion started slowly, but as the time passes, it is now expanding much faster. So this is a surprising point which was brought in by Hubble. So the fact is that we are expanding, but we are accelerating. The understanding of accelerating universe is about 100 years old, and after that, scientists have been basically trying to find out what is the speed, and this has become a very important aspect of understanding our known physics. Even though we have Einstein theories, we have Neil Bohr theories, we have different theories explaining in quantum mechanics, but none of this will matter if we don't understand what is going on with the universe. And that is why it's a big mystery that we need to solve.
Definitely, it is a mystery because there's one thing which is also very unique, because there's a discrepancy in the expansion of the universe. At some place it is expanding fast, at some place it's expanding slow. Before I go forward, we have Sandeepa Kaista, and she's saying hello, and Madam, good morning, Sandeepa. In case if you have any question regarding this topic in our science show, please feel free to put forward. We will be able to answer. We will try to answer your question. And we also have Tanmay Hazara, so welcome to this show. So as Chandrakant, we were discussing that there is a discrepancy in the expansion of so is there any unique cause of this, or we are still doing research on that?
Well, we are doing a lot of research on this because, first of all, the big challenge is to find, if we are expanding, then what is the rate of expansion? Because we need to determine whether the universe is going to end tomorrow, or after trillions of years, or maybe billions of years. We don't know. What is the end result of the universe? Is it going to end? Because if the universe had a beginning, will it end? And when will it end? And that is why we need to find out at what rate we are expanding. Also, if we are expanding, then till what point we will expand. That means all the galaxies will start seeing each other, and in future we may not even see this night sky as we see it today, because the universe would have expanded and things would have expanded so much that all the objects in the universe would stop seeing each other. So to understand this aspect, it is very important to do a lot of research, and that is why we are talking about why we need to know exactly how the universe is being shaped. As in this picture, initially the universe was more of a hazy cloud kind structure, but as it expanded, it started forming a filament structure as we see it today. But in future, this filament will be permanent. The filament where you see these filaments where the large cluster of galaxy exist, and there is matter which is gas or dark matter which exist. So in future, will this expansion even break open these filaments, and then all these different individual aspects of the universe will go their own way? That is why we need to understand this. And Hubble started this whole observation from his home-based observatory. While looking at the Andromeda, he found that Andromeda and other galaxies are actually receding also from a central location. And then that is why this aspect is also known as Hubble constant. Understanding at what speed the universe is accelerating away from each other is known as Hubble constant. And that should be a constant figure. The rate of expansion. I'm not saying that the speed at which we are expanding, because it is ever increasing, but the rate of increase should be constant. And that is what for last 30-40 years, scientists have been very, very busy in finding out what is the rate of acceleration, because if it is not constant, then we have a serious issue at hand. Then we will not be able to basically define, none of our formulas, physics formulas will work, because the basic premise of understanding Big Bang and at what speed we are expanding will be completely wrong. Even though relativity will still hold, but the basic law of motion, law of gravity, none of those things will hold water. And that is why it is a big mystery to find out a constant. And scientists know about this, and they have been able to use different techniques to find this constant, but they are getting different figures. As you rightly pointed out, Kanchan, that the rate of expansion using different experiments, you get different results.
Right.
And that is what the crisis is all about. So that is why we call this a crisis in the cosmology, because we don't get a constant figure. If different part of the universe is expanding in a different rate using different experiment, it shows us x value. The other experiment shows us a y value, and we need to know exactly which experiment is wrong, which is right. For instance, the cosmology, the Hubble constant is calculated in the terms of kilometers per second, the speed at which the universe is expanding, per parsec, megaparsec. So 1 megaparsec is equal to 3.3 million light years. So it's a very, very big measure. Kilometers per second per megaparsecs. So if the expansion is calculated using this unit, then you can cover a lot of ground, and you can say that, okay, universe is a big place, but it is also expanding at a higher rate. So this is the way the Hubble constant is calculated so far. So there is nothing wrong in the unit.
So actually, this is a great mystery, because if we are able to come out of this mystery and we have the data, I think that will solve a lot of other aspect like black energy, or kind of Big Bang, the process of Big Bang, because there are some scientists who are also saying that Big Bang never happened. But that is also one of the ideology which is surfacing parallelly with all scientific findings regarding space is happening. So it will be great help to find out the force which is driving this universe, and in which we are a tiny entity. So do you want to add more regarding this mystery of the expansion of universe?
Well, Kancha, this is a very important question, and in fact, thanks for pointing that out. You see, when we found that the universe is expanding, there has to be some force responsible for this expansion. Similarly, we have gravity, which brings things together.
Right.
And we found that the gravity is not only the byproduct of the matter that we see in universe, it is also, there is something called exotic matter, which is also known as dark matter. Now, we will not talk about dark matter and dark energy in this live stream. It requires a totally different, much detailed explanation. But for the sake of understanding the Hubble constant, let's stick to that there is dark matter, and which brings things together, which binds things together, and because of this dark matter and the matter of which we are formed, like electrons, protons, etc., we are formed of that. All the stars, all the visible matter is formed of matter. And there is something that we do not see, is called dark matter. So matter brings things together and form different objects in the universe. If it is expanding outwards, that means there must be another force which must be present in our universe responsible for expansion. Because in our universe, things do not happen without any explanation. There has to be something to drive something. For example, heat and cold. There has to be, heat and cold is nothing but kinetic energy. So we know exactly elementary school level that from hot areas, the kinetic energy travels to cold areas. That is how the universe works. So if something is hot, it will eventually become cold over a period of time. So we know exactly what is the reason for that. Similarly, why planets are formed. We know that this is gravity. Why we are able to walk on Earth. Why we are able to send spacecraft in universe, and what orbit they will take or what trajectory they will take. We understand all that. Similarly, if the expansion is happening, there must be a force. So we don't know what is this force, and lack of good name, scientists call it dark energy, which is opposite of gravity.
Right.
And it is also known as 0-point energy, which is in our Hinduism actually. There is an explanation of this dark energy for a very long time, and it is called Adi Shakti. We worship this energy. So that means the ancient Hindus knew about this force. They knew about the expansion, and even they didn't understand what is this energy, so they called it Adi Shakti and started worshipping it. But today we know that there is a energy which is responsible for expansion, and it is our scientists' endeavor to understand this. And Hubble constant, which is at what rate we are expanding, will give us a lot of insights in understanding the dark energy. We will be able to determine what is the force of this dark energy, what creates it, what is the and how does it affect other things like nuclear forces or gravity, how this is anti everything else in the universe, right? So did I answer your question?
Yes, you did actually. I also want to add that and dark energy is not a reactive aspect, as scientists say. It doesn't react to anybody as the other mass, other mass react. So it is quite an unknown field, and still scientists are working on that. Before going forward, I just want to name Lalita Vasavraju, Martini Tini, and Anshul Rajput, who are watching this stream. So do you have any question regarding cosmic expansion? Please go forward. We'll be happy to answer. So going forward, let's also understand little bit about cosmic expansion, which will I think our audience will understand how things are working in space.
Well, bigger the value of the Hubble constant will give us that the expansion of the universe is also much higher. So if we know that if the universe is expanding at a higher and higher rate, then the end is quite near. End of the universe is near, and that information is very important for our own existence. How long we have, how long our civilization have, or different universe has before it ends, and even if it ends, how it will end. So there are a lot of questions which can be answered by if we know exactly what is this Hubble constant, and that is why it is important to understand the Hubble constant. And one of the method is using the microwave background. So people who are interested in the science, and if they have little knowledge about space, this is a microwave background which is omnipresent. See, whenever if you switch on the TV, and many of us would have seen this wide haze coming on the television screen with a very crazy sound. And also, whenever if you are used to radio, whenever you try to tune in radio and you don't get any
Frequency.
channel, any frequency, you get this hazy sound. It's very crazy, which so you get this sound in any radio or any television anywhere in the world. So scientists started observing this is something which is omnipresent, and in the 1960s they actually were able to picture that this is the cosmic background, microwave cosmic background, which is constant across the universe. And this is a picture they were able to take, and that's how they found that this is the leftover of the Big Bang, and this is the evidence because based on which we believe there was a Big Bang. This is a leftover glow of the Big Bang, because we don't know what the Big Bang, the light of Big Bang is not visible, but the leftover of that is visible. This is the microwave which was created by the Big Bang. Now this is a constant feature. We have been able to take the picture of our universe, and wherever you see the darker patches, you don't see matter there actually. So we know that there is less matter in the dark blue areas and dark areas, but wherever there is red and yellow and green picture, as you can see in this one, there is matter. That means the galaxies, gases, planets, stars exist in this area. So so this is a cosmic microwave background, roughly 300,000 years after the Big Bang, and that is a constant picture. Now, when we say that this is a constant, it has also changed over time because things keep moving in space. So by observing this picture, you will think that why we are looking at this static picture, but by observing how this picture has evolved, we can actually know exactly how things have moved. These red dots or yellow dots or blue dots in this picture, how they have moved. So we can actually plot this trajectory, and looking at those motion, we can find out that what causes this motion. Otherwise, if things are not changing, then they will be static. But they are not static. So looking at this image, we know exactly how things are changing, and that is how we actually looking at these minute changes in the cosmic microwave background, this fluctuation in temperature, because a cosmic microwave background is nothing but a temperature map. Hot things are red and yellow, cold things are blue. So looking at this motion of these dots in the picture, we will be able to understand how these hot areas are moving, and that way we can trace back our using the mathematic formula, we can trace back our using the formula, find out where they were 300,000 years after the Big Bang, and after 3.8 billion years, where are things today. So looking at the difference in motion, we will be able to find out at what rate we have expanded. So this is one of the methods of finding out the Hubble constant, and this method gives us a Hubble constant of about 67 to 68, because whenever we apply some statistical formulas, there are some averages. So 67 to 68 kilometers per second per megaparsec is the value that we get. So the problem solved, scientists were able to find that okay, now we have a picture based on the microwave cosmic microwave background, and this should be the real thing. But in scientific community, you're not satisfied. You want to cross-check your values, and that is why, even though this method gives us a picture of 67 to 68 kilometers per second per megaparsec, for the viewers who have joined right now, let me tell you, 1 megaparsec is equal to 3.3 million light years. So 67 to 68 kilometers per second per megaparsec is a huge speed, the speed that you can't even imagine. That is the speed of expansion of the universe. And that is accelerating. So at this speed, we are accelerating. So actual speed may be higher than this. So that we found actually. However, scientific community said, okay, how do we prove that this is the only right method? Or is it the end of the theory? Is it end that we have been able to find the actual rate of expansion of the universe? So there are other teams who started working using some other method. And that method was involving observing type A1 supernova. Now, type A1 supernova is very specific. So again, let me take a detour and explain very briefly what is type A supernova. See, whenever a neutron star actually gather more matter, more than 2.5 times the mass of Sun, explodes into a supernova. Now, since neutron stars are very, very tiny objects, but whenever it crosses the Chandra's limit, Chandrasekhar was a great Indian scientist who also was a Nobel laureate. So he gave a limit that if the star exceeds certain limit, there is no power in the universe which will prevent it explosion. So whenever the neutron star explodes, once you form a neutron star, then it lasts for millions of years in that form. But if it gathers more mass because of whatever reason, and if it crosses Chandra's limit, it will explode and become a black hole. And since there are set mass, you look anywhere in the universe, the Chandra limit for neutron star it's just 1. So whenever there is a neutron star exploding and becoming a black hole, that explosion is very similar. So you can say that these type A1 supernovas are similar to each other. If there are different parameters in the universe, they will actually be different. But this one is constant. Whenever there's a neutron star exploding into a supernova, it will have a constant brightness, constant explosion, constant everything. So it's like a beacon in the space. So scientists know very well that there is a type A1 supernova. The illumination, the energy released will be constant, and we know what is that constant. So if we are observing that, and you also know that if it is a far off supernova, then the light will take longer. So looking at that parameter, we can then find out if there is a far off type A1 supernova, it has taken so many millions of years to reach us, and in the process of the light reaching us, it has also expanded because the light has taken more time to reach us. Using this method, we can find out. That's the second method to find the Hubble constant. Any question, Kanchan? I've been talking for quite long.
Yeah, actually, I just want to add here that if we are able to find out the mystery of this Hubble and the expansion of universe, I think we will be also able to work and find out the mystery of black hole and quasar, and that will really help human species because now it's a quite prevalent, and we most of the fraternity who are working on space, they want to go and settle and maybe establish the mankind in different planets. So I think that is a very good and very good chance to really come out with the explanation of this expansion in the cosmology.
Of course, I mean, this is a starting point. We have reached so much. We have achieved so much. We know so many things, but none of these things will matter or probably undergo a lot of change. Our understanding of physics, if the expansion of the universe is not constant. So that is why this is also known as crisis in cosmology. It's a big challenge to find at what rate we are expanding, and therefore, the using this type A1 supernova method, as I explained, that the brightness is constant across the universe, and using this method, the the Hubble constant has been found, but using this method, there is a different, results we get. We get 71 to 75 kilometers per second per megaparsec.
Okay.
Now, you may think that it's not a big deal. In the previous one, we were getting 67 kilometers per megaparsecs, and here we are getting 71. So, only difference of 5 kilometers. But remember, this is per kilometer per second per megaparsecs.
Okay.
And 1 megaparsec is equal to 3.3 light years. So, difference of 5 per second per megaparsec. That means every second 5 times 3.3 light years expansion is happening. So it's a big difference. If it's like a point variation, 0.1 or 2, it is okay. Then we know exactly the first method worked. It's a substantial difference, almost 10% difference. That means the speed of expansion or the acceleration of expansion of universe is 10% higher using the second method. So these two method of calculating the Hubble constant, individually you cannot pinpoint any mistake in them. From mathematical standpoint, from scientific community standpoint, from scientific methodology standpoint, both of these methods are perfect, pristine. They are following the best practice, and scientists have actually repeated this to cross-check because many times your observations can give you wrong pictures. They have traveled to different parts of the Earth and conducted these experiments. Every time they get this difference. So it is baffling that why we are getting these two different pictures, two different results for Hubble constant using two different methodologies. Ideally, if we use different methodology, if it is a constant, we should always get a constant. That means same value we should get. But in this case, we are getting different values.
Right.
And that is why, this is a big challenge, to try and find out a sort of equilibrium between these two methods. That has been a challenge for last 50 years nearly, where scientists are trying to find some solution for it, because we keep hearing about new discoveries. We have found this on Mars, we have found this on Venus, we have found this the super Earth somewhere 140 light years away.
Right.
But this is keeping people engaged. But heart to heart, scientists know that if none of this will matter, even if you have to take a flight to Alpha Centauri in future,
Right.
the Alpha Centauri would have expanded. So our calculations will go wrong.
Right.
Suppose today we are planning to go to Alpha Centauri, it will take 4 light years. But then by the time we reach there, it would have expanded. That means where we intend to find Alpha Centauri, it has moved on.
Right, it's quite a critical situation. We are really planning to go and the space, which is a final frontier for human beings. So it is quite a challenging aspect of universe study and cosmology.
Absolutely. So that is why it is heart to heart. Scientists want to resolve this issue and move on, basically.
Right.
So therefore, scientists then use a different methodology, and this is called the Hubble tension. It's a crisis in cosmology, but also known as Hubble tension. So different names are given for this.
Right.
So people are trying to find out a new method. Now, a team of scientists have suggested a third method.
Okay.
And that involves the gravitational lensing. So we know that universe is full of these large lenses. When we look at telescopes, we actually create these glass lenses. Like I am wearing this one of the lens here. It is in my glass. What this lens is doing is actually helping me focus light and making me look clearly. Similarly, if you look at through your telescope, it will magnify things. It will expand the light in such a way that you start seeing things, far off things, much closer to you. Right? This is a simple mathematics or simple physics of telescope. However, scientists found that if there is large gravity area, for example, a star or a black hole or even cluster of galaxies, that cluster of galaxy will create gravity, and we know that gravity affects light. So if you look at something which is behind that high gravitational area, we know that this cluster of galaxy will create a lensing effect, and that this process is called gravitational lensing. The light will actually go around and bend and will reach. The net effect of this kind of observation will be similar to what we see through a telescope. So in nutshell, there are natural telescopes available in our space which are now very actively used by scientists to look at far off objects. And using our own telescope, scientists are now not using direct. They are now using Hubble, using James Webb telescope. They are trying to make use of gravitational lensing and start things which are sort of hidden behind these gravitational lenses. And we start seeing these images.
With the new findings, scientists also said that there are very small clusters in a couple of the parts of the universe which were made at the time of a Big Bang. So that is also a point of research, and still scientists are working why these clusters are so old. Clusters are available in the pockets of universe, and they are not one or two, but they are immense clusters. So that is also a point of study and research. I think that will also add on to the expansion of cosmology, expansion of universe, which is just happening, and we are still in kind of confusion because we are not getting a right equation for that.
Absolutely. So basically, using the second method, scientists are able to evaluate that when they see these pictures of very far off objects, they know exactly, because everything is moving. So they will be able to see these pictures in different times. So using these, gravitational lensing method, at different times they will see a different picture. But the frequency of when they will see this can be determined very clearly. So it's a big process. So if I start explaining this big process, it will take a lot of time. But for the sake of simplicity for the viewers, anything which is behind a high gravitational area, anything behind that, the light will actually converge and then come towards Earth. In fact, it will be much more clearer if I show you the next picture. So in this one, there is an area, there is a galaxy behind a large gravitational picture. The light is converging towards the Earth. And when light converges towards the Earth, we start seeing this galaxy which is behind the high gravitational area. Now, this is sort of magnified, and we start seeing this. So if you actually use conventional method, you will not even see this galaxy. But if you use the gravitational lensing method, you start seeing this. And when things move around, because Earth is here, then after some time it will be here. You again focus your telescope, then you see a totally different picture. So by measuring the Earth movement and also measuring the movement of the other different bodies, we know exactly how we will be able to see this object using gravitational lensing. And using this mathematical calculation, we can find out when we see different images, when we will be able to see the time difference can be very accurately predicted using relativity, the theory of relativity. So using this method, scientists were able to find that if the universe is expanding, even this galaxy will be expanding. Even the the galaxy cluster in front, which is creating the lensing effect, will also be expanding, will also be receding away. And so all these images will also undergo some changes when we observe them from Earth. So using this method, they can also calculate the expansion rate. And using this gravitational lensing, you can actually calculate at what rate the expansion may be happening. But remember, these objects that we are watching using gravitational lensing are very, very far off, extremely far off, like almost at the beginning, almost at the edge of the universe. Some of these objects can be 20 to 30 billion light years away from us. Very, very faint, which is very difficult to even see. We are able to see these objects only because there is a natural lens available. Universe has provided us using gravitational lensing. We can see this. So since these objects are very far off, we can actually predict at what speed they are receding, because the chances are they may be going away from us at a much higher rate. So it's a lot easier to calculate the Hubble constant using this method. And surprisingly enough, they were able to find the value, which is this 63 to 70 kilometers per second per megaparsec, which is similar to the first method of looking at the cosmic microwave background. So at least in the third method, which is a recent development using the gravitational lensing method, we have some sort of agreement. But needless to point out that this is not the end of the story, because this is a new method. We need to do a lot of iteration, and we need to agree that this method works every time and give the same result.
Right.
So while there is an agreement, at least two methods gives similar Hubble constant, the rate of expansion. We know that these are the two methods. There could be a fourth method, we don't know. The scientific community is working very hard to basically create more iterations, coming out with much more instances of calculating using the second method, using gravitational, so that every time it should give a constant. Whenever we say something constant, it should be constant. Every time we should get the same figure.
Right.
So at least in the third method tallies with the first method of calculating Hubble constant using cosmic microwave cosmic background.
Right.
So if there are two methods giving the same result, we will know exactly what is the Hubble constant, what is the rate of expansion of the universe. Kanchan, do you have any last observation on this?
I actually had been reading regarding this for a long time, and there is one gap. I think the scientific community, the space scientists they are working, and because that is an essential calculation, essential part of space travel. And that is very much required. And before I go further, we have Yasmin, we have Batul, and SK Zaid, MD, and Miss Yadav. So welcome to the show. In case if you have anything regarding this science show, and if you have any question regarding cosmology, please go forward. We will happy to answer you. So as I was telling you, Chandra, that yet a lot of research is required, because this is critical for space travel. And it is really critical when we are also making our base in the space, and then from that base we are trying to travel to the far planets and want to observe the different stars. So I think this is one thing which we have to keep track, and we have to know, and we will be sharing the latest finding regarding this to our audience in near future.
Absolutely. So every Monday we will come with science show. This is a live stream, so kindly join if you want to find out about the secrets of the universe. Today we covered at what rate the universe is expanding. Next Monday, same time, 11 a.m. Please join back. We will bring another scientific explanation about why things are, how things are, what is happening next, and it will be very interesting for your participation. Nevertheless, if you have any questions regarding this subject, you can actually share your comments even after the stream is ended. Otherwise, we are here to, if you have any question right now, we will hold on before we end our live stream and answer your question.
So it was quite a raising point, and it was a quite interesting discussion as far as me is concerned, and I think my audience will also enjoy this. So we'll be meeting again on Monday next week. Till then, you take care, be happy, and keep doing good work. Bye-bye.
And don't forget that science and physics is the hallmark of our life. So with this closing comment, bye-bye.
Bye-bye.